The first allotrope of carbon we will discuss is diamond.
So diamond, that is the simplest form of diamond. It's called tetrahedral. Looks like this, okay? Except imagine all four of these. 1, 2, 3, 4, the yellow one. Imagine all 5 of these are black, okay? Black is carbon, yellow is hydrogen, but imagine all of these are just carbon atoms. So carbon atom, carbon atom, carbon atom, carbon. So all of these are carbon atoms, and they're all covalently bonded. You don't know what that means yet, but they're all bonded to each other, very strong, okay? What happens is these now repeat like 1,000,000 times, probably more than that, okay? Repeats over and over and over and over, and it forms this big crystal, this 3-dimensional crystal. It's called diamond.
The diamond structure, each carbon atom is connected.
So I'm going to kind of speed this up here. See, it starts to build, it gets bigger and bigger and bigger, so it ends up looking like that. Okay? So that's what diamond looks like if you were to zoom in and look at the molecular structure. And you can see the shape. That one's kind of distorted. Hold on. Nope. Okay, right there. Pretty close. What's that shape look like right here? Hexagon, right. Forms a bunch of hexagons repeating over and over and over. So that's diamond. That's what diamond looks like. Next is graphite. I don't want to talk about that other one. It's basically the same as diamond. Here's graphite.
Graphite is quite different from diamond and lungstallite. In the graphite structure, each carbon is connected to only 3 atoms. Since carbon must always form 4 bonds, one of the 3 bonds must be a double bond.
So, yeah, if I take one off of here, so 1's bonded to 3, that's the difference between diamond and graphite. And graphite has these things called double bonds. So this carbon atom is bonded to this one, and this one. So 3 bonds. You can count, they're all bonded to 3. This one would be bonded to something else, just not showing that. So this is what graphite looks like, but it's more of 2-dimensional. It's not really 3-dimensional. It actually forms like sheets. So this would be one sheet. This thing here on the screen would be one sheet, and then have another sheet below it and above it, and then it would alternate. And these sheets of graphite kind of hover near each other. They don't touch. In between them, forces of attraction. So in between those sheets are weak forces of attraction. Why weak? Because if you rub your finger over a pencil tip, you get graphite on your finger. What happens when you write with pencil or rub it with your fingers, or if it comes in contact with anything, these sheets break off. So when you're writing with pencil, you're breaking sheets of graphite off. So the sheets keep sliding off of each other, and that is why you can write with it. That's why it's fairly weak. Diamonds you can't write with because they're all very strongly bonded. Here, they have these sheets that are weakly held together. So they show a good picture of that here. There's a bigger graphite. Here we go. Right here. So green, blue, green, blue, green, blue. That's just showing the alternating sheets of the graphite, and it's in layers. So you can see that space. So what's holding them near each other? Forces of attraction, like gravity. Okay? That's the concept. And these sheets, again, are weakly held, so they slide right off. They break off of each other. That's why graphite is a lot weaker than diamond and why you can write with it. And the last one is buckyball. And where the heck is it? There it is. So there's buckyball, or Buckminster fullerene. Basically, if you take those sheets of graphite and kind of roll it up into a ball, that's basically what this looks like. Okay? Kind of. It's a little different, but you can see 1, 2, 3 bonds, 1, 2, 3, and they form the hexagon shape as well, but it's a ball. It's a little ball. So that's called buckyball. If anyone has ever heard of what's called carbon nanotubes, it's these long, thin tubes. Actually, I have that right here.
This atom to that one there, you get a semiconducting nanotube.
So there's a nanotube. So he took kind of one of those graphite sheets, and it's just, this person did this like, with a piece of paper, but this happens on a much smaller level, so it's curved into like a tube. It's called a nanotube. There's another thing carbon can do. It's called graphene. You can make your own graphene. What the heck is graphene? It's a very thin, 1 atom thick sheet of carbon. 1 atom thick. Atoms are ridiculously small. The way you can make it, take a piece of paper, shade it with a pencil. Take a piece of Scotch tape, put it on top of that shading. Peel the tape off. So now the tape has graphite on it. Usually part of the tape has graphite, the other part, half of it would be graphite, half of it would not. So you peel the tape off, half has the graphite, half doesn't. You take the tape and fold it on itself, and then peel it apart again. That's where you get your 1 single atom thick of carbon, which kind of looks like that if you were to zoom in. But that's called graphene, and that's what this is about, graphene. Why is this called Graphene Revolutions? Because graphene, they think, is going to be used to make bikes, planes, TVs, cell phones. It's extremely light, conducts electricity, and it's very strong. Kind of like buckyball, so it all started with this. But that's it. Those are the 3 allotropes: diamond, graphite, buckyball. Questions before we write some more stuff down in our notes? All right, lights please. Can you guys get the blinds again? Let's finish these notes up today. You will not have any homework, unfortunately. Don't worry, the rest of the week you will. All right, so diamond, very strong, high melting point, Thanks. Diamond, very strong, high melting point. All carbons bonded to each other. Graphite, sheets of carbon attracted to each other with weak forces. So again, diamond's more like a 3-dimensional shape, whereas graphite is just the sheets layered on top of each other. And then buckyball, 60 carbons, 60 carbon atom, we'll say soccer ball, in quotes, because it's not literally a soccer ball, but it looks like it. All right, and again, the properties are very different. So let's write that over here. Different properties. They all have different properties. You know this though. Diamond looks different than graphite. We use diamond for different things than we use graphite. And buckyball, like I said, looks like soot. So they all look different. They all have different properties. Why? Because they're arranged different. Okay? They're arranged different. Questions? No questions. Everybody's good to go. All right. Can I erase this?
Yeah.
Anybody want me to not erase it? Okay. Can I erase the top part? I can erase the top part. All right. So next, we're going to zip through. Got about 5 minutes left. We're going to go quickly. Did we talk about the Honkelbriefs?
Yeah.
No, we didn't.
Are you sure?
The 7 diatomic elements?
Oh, yeah, we definitely talked.
7 diatomic elements. I didn't think we did. The 7 diatomic. There are 7 elements on the periodic table that exist in pairs. They're like twins. And I call them Honkelbrief. H-O-N-C-L-B-R-I-N-F. Honkelbrief. Just it's a little acronym. Honkelbrief. Hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine all exist like this. Pairs. Each little ball is an atom. So hydrogen gas in the air, or in a tank, it's floating around like this. Pairs of H's, two H's together. Oxygen gas, we're breathing that right now. O2. They're in pairs. So all of these get little 2's, N2, Cl2, Br2, I2, and F2. All of those elements in their natural state are in pairs. They're called diatomic because they're reactive, so the individual atoms can't really exist on their own. They want to pair up. It makes them more stable. They're more stable this way, so they exist in pairs. So what do you need to know? The 7 diatomics. That's what you need to know, and that's why I come up with the acronym HONCOBRIF. Okay. So those are the 7. Moving on. Let's talk about, let's see, what was next? I think silicon's on my list here. Yeah. Silicon. It's the second most abundant element on Earth. There's a lot of it in the ground. It's also found in the compound SiO2 solid, which is also known as quartz or sand. Pure sand is SiO2. I can order sand from a chemical company. I know it sounds weird, but you can. And they give it to me in a container, and the compound is SiO2, silicon dioxide. That's quartz or sand. This is extremely hard too. It's similar to diamond. Similar to diamond in the way it's arranged. Why? Here's why. What group is silicon in? 14. Guess what else is in group 14? Carbon. That's what diamond's made of. So it makes sense. Similar properties, right? Let's see. What else? Oh. Silicon's used in computer chips and photovoltaic cells. What the heck is that? Photovoltaic cells. PVC. That's different. PVC pipes are not what I'm talking about. Photovoltaic cell. Solar panels. That's where they're used. Solar panels convert sunlight into electricity. Computer chips as well. Silicon conducts electricity but doesn't get as hot as metals because it's a metalloid. It's a metalloid, so it has properties of both. Non-metal and metal. Okay. That's it for silicon. I'll leave that up in case you still need to copy some things down. Nitrogen. We just learned is N2 gas. Nitrogen, essential to all life. And I want to say it's about 78% of the air. 78% of the air we breathe is N2, nitrogen gas. Guess what about the other 20% is? Oxygen, right, so I'll put that over here. Oxygen. O2 gas. About 20% of the air. This is the most abundant on Earth. It's in the ground, certain compounds, it's also in water, it's also in the air. O3 gas. Don't breathe O3, it's way up, protecting the Earth. What is it? Ozone. Don't breathe that. Breathe O2 and you're good to go. O2 is good for you.
Why can't you breathe ozone?
Because it's not O2. Your lungs, your body wants oxygen gas. This is ozone. You breathe in ozone, it's like poisonous. It's like CO2, carbon dioxide, or carbon monoxide. Won't work. Won't work with your lungs. Okay, so that was oxygen. What else? What else? Oh, hydrogen.